next we will start with logic and fault simulation. So, this is basically some software tool that has to be designed for checking for getting confidence about the goodness of this module with the test pattern set that we have generated or that we are using for testing some system. So, it will go through this flow. First we will have an introduction, then the simulation models, then logic simulation, fault simulation and the concluding remarks. So, logic simulation, it predicts the behavior of a design prior to its physical realization. So, what happens is that suppose we have got a circuit to be designed. So, we have generated some test pattern set for that, and now how do I judge the quality of this test pattern set? One possibility is that once the design has been obtained, once the design has been fabricated, if the chip has been manufactured, so we can apply those test patterns and see whether it is detecting some faults that might have crept into the system and crept into the chip, and do I get a confidence, okay, it is able to detect those failures. So, if it is true that for all the chips that are detected by this process, they are really faulty, then we are happy. Our tool, our test pattern generator could generate test patterns for this purpose. Or it may so happen that for all the defective chips, our tool also, our testing process also tells that they are faulty. So, that is the other avenue, and in which we can say that our test patterns are good, but that is far away, and in fact, that is after the chip has been manufactured. But can we do something so that before this manufacturing is done, so we can get confidence about the goodness of the test pattern set that we are using. So, this predicts the behavior, this logic simulation problem. So, this predicts the behavior of a design prior to its physical realization. So, this is basically the problem of design verification. So, specification is there. So, it goes into manual design or via synthesis. So, it may be manual design or maybe by synthesis tool. So, it gives the circuit description. When this manual design is going on, side by side it also goes into a test bench development. So, in the test bench development, so it will figure out like what are the what may be the possible input patterns that may be that will be applied to this system, and what are their correct responses. So, they are actually forming this input stimuli and expected responses. So, this test bench development process comes up with these two output, input stimuli and test bench responses. Now, after this circuit has been synthesized, or the circuit, so the system has been synthesized. So, we have the circuit description. So, this circuit description we simulate with respect to this input stimuli. So, till now I do not have the actual chip manufactured. So, I have got only the description of it after the synthesis has been done. So, the description is simulated with that input stimuli, and accordingly we get the simulated response. Now, this simulated response we compare with the expected response, and if these two from these two we do a response analysis. Now, if these two responses are not matching, that means there is a bug. So, if there is a bug, that so we need to correct. So, what do we need to correct? So, we need to correct this design process, and that way again this it will go through the modification, it will do the synthesis, and it will go on like this. However, if there is no bug, then of course, we can go to the next design stage, that may be the actual implementation of the circuit and all that. But what about the quality of the test bench that we have developed? So, with respect to a given set of test bench, we are getting the confidence that okay, there is no bug in the system, but it is actually the system does not contain any bug which could have been detected by this particular test bench. Only this much is the confidence level. So, to have a better confidence, the test bench development should also be judged. So, they need to be judged like how good or bad is this test bench. So, this fault simulation, it predicts the behavior of faulty circuit as a consequence of inevitable fabrication process imperfections. So, it tells like if this particular fault has occurred in the circuit, then if you apply this particular pattern, so you will get this type of output. So, that is the fault simulation. So, this is a very important tool for test and diagnosis purpose, because it can tell us like what is the fault coverage. Like if I apply this test pattern set, how much is the confidence that my circuit does not have any of those modeled faults. As we have said that if there are n lines and we are considering single Stuckart fault model, then there are 2n possible faults. Out of these 2n possible faults, how many of them are getting detected by my test pattern set. So, that may be the type of confidence that gives us. So, that is the fault coverage, and also it gives us some way to diagnose the problem. Like it may so happen that some test has failed, in the sense that we applied some pattern to a circuit for simulation or at the manufacturing stage. So, we apply the pattern and we see that the fabricated chip, it has failed that test, but why has it failed? So, from the faulty response, we should be able to trace back and see where exactly is the fault. So, that is actually the problem of diagnosis. So, at the fault simulation, it can tell us like if you get this type of behavior, then possibly the fault is somewhere here. If you get for this pattern, so if you get some other response, then possibly the fault is somewhere else. So, that helps us in pinpointing the fault locations or locating the faults. So, they help us so in estimating the fault coverage. This fault simulation, it helps us to tell give us the confidence how many faults are what is the percentage of faults covered. Then fault simulator, like it is simulating the faults, like what type of faults we can simulate as a single Stuckart fault, multiple Stuckart fault, bridging fault, etc. It can also help us in test compaction, because we know that for the one particular fault may be detected by a number of patterns. So, it may be true that I do not need to apply all those test patterns for testing a particular fault. So, can we select a subset of test patterns from a given set, so that all faults are covered, but we do not apply all the patterns. So, that is actually the process of compaction. So, that can be done to reduce the test application time and test data volume. And fault diagnosis, that we have already discussed. So, in the manufacturing process, if there is some problem, then this fault simulation, it can tell us like where exactly the fault may be located. Simulation models, the first one is the gate level network. So, we can think that my circuit is at gate level. So, it is interconnection of logic gates. So, like this, here we have got this circuit with 4 gates. So, that may be gate level network. For sequential circuits, so output will depend both on current and past values. So, this may be the model. So, we have got this primary input, primary output, pseudo primary input through this yi lines, and pseudo primary outputs to this capital Y lines. Okay. So, this may be the model for the sequential circuit. A positive edge triggered D flip flop. So, it may be the actual circuit may be like this, but in terms of block diagram. So, we may look at it like this, that if the clear line is high, clear line is low, then this Q will become low. If this preset line is low, then this Q will become high. So, this logic gate circuit actually is modeling that. Most of the time we will be using these symbols 0, 1, U and Z. So, 1 and 0, so they are known from our binary logic. So, they are true and false of that Boolean algebra. Then U is unknown. At when we are trying to see like what may be the value of some input, what will be the value of some point in the logic circuit. So, that may be unknown. For example, you say if we consider this circuit and all on a sudden we ask what is the value of H, without telling explicitly what are the values of A, B and C, and simulate and trying to figure out the value of L and E. So, at that point of time the value of H is unknown. Okay. So, that unknown is sometimes used to represent that the unknown logic state. It may be 1 or may be 0, and there is another logic state which is Z, or high impedance. So, they are not neither connected to VDD nor connected to ground. So, they are neither 1 nor 0, but U means it is either of them, but it is unknown. Z means it is high impedance, but it is not connected to either of them, VDD or ground. In terms of ternary logic, so we can define this AND, OR and NOT functions, like say in an AND gate, 2 input AND gate, if one of the input is 0, then the output is definitely 0. So, one of the input being 0, output is 0. Similarly, one input being 0, output is 0. If one input is U, then the output depends on the other input. So, if other input is 0, it is U. If it is 1 or U, then it is U. Similarly, here also it is like this. Similarly, for the OR gate, we can make the corresponding logic table. Okay. So, 0 and U is U, 1 and U is 1, because whatever be the value of U, so it will become 1. So, like that we can do it. Similarly, NOT, 0 converts to 1, 1 converts to 0, but U remains U only. Now, simulation based on ternary logic is pessimistic. Why? A signal may be reported as unknown when its value can be uniquely determined as 0 or 1. So, here it is say this one, say if we follow this circuit and suppose the value is 1, U and 0. So, this is unknown, as a result by the OR logic, since this is unknown, so I have to make it unknown, and in this AND gate one input is 1, another is unknown. So, this is also unknown. Since this is an inverter and one input is unknown, so output is also unknown, and this NOR gate, so that is also unknown. So, if we follow a pure ternary logic based simulation of this circuit, then this is the situation, that many of the points are remaining unknown. Now, you see that unknown is basically 0 or 1. So, what we can say, instead of U, if we write 0 or 1, so at this G1 I cannot say what it is. So, it remains at 0 or 1, that is unknown. Similarly, at this point one of the input is 1. So, whatever it is 0 or 1, so that 0 or 1 comes here. Similarly, at this point 1 or 0 comes. So, if this happens to be 0, then this is 1, and this, if this happens to be 1, this is 0. So, from this I can find out that these two values are never same. So, as a result, this NOR gate output will always be 0. So, that way we say that the ternary logic simulation is a bit pessimistic, but accepting that, so it helps in many cases where the values of logic different signal lines are not known. So, doing a simulation at that point of time, so you have to go for ternary logic. Another is the high impedance state. So, tri-state gates, they permit several gates to time share a common wire like this. So, we have got say this G1, G2, G3. So, these are all tri-state gates. So, this if E1 is high, then this X1 will be coming to the output O1, and that this O1, O2, O3. So, they are actually connected in a fashion. Now, Y equal to Xi if Ei equal to 1, and Y is Z if Ei equal to 0. So, that is the thing. Now, this whole operation, so there may be, so this is connected here. So, and now when more than one of these devices are on, more than one of these buffers are on. So, what happens at this point? So, that is defined by the resolution function. If all of them are high, if all of them are disabled, so E1, E2, E3, all of them are 0, then we may have a pull up or pull down mechanism by which this bus will be high or low. So, pull up will make it high, pull down will make it low. Then it may be fed to some D flip flop, or it may be fed to some other combinational element. So, anything can happen. So, it will go like this. So, this the sequential, it may go to some other circuit input. Okay. So, this pull up or pull down elements may be there. Now, resolution function will tell us like how do you get the logic at this point if multiple drivers are active. So, there are wired or wired, and so we have seen many such models. So, any of those models can be followed, and it depends on the technology that we are using, like what will be the resolution function. So, bus conflict occurs if at least two drivers drive the bus to opposite binary values. So, this is the bus conflict. To simulate this tri-state bus behavior, one may insert a resolution function for each bus wire. So, we can say that okay, this wire will be resolved using wired AND function, some other place we may say that okay, this will be resolved using wired OR function, depending upon the type of implementation that we will finally have. So, this simulation it may report only occurrence of bus conflict, and they may utilize multi-valued logic to represent intermediate logic states as well, including logic signal values and strengths. So, that can also be done, like if we instead of having this 2 level logic, if we have got multi-level logic, then we can have a simulation with this intermediate logic states. Now, this logic element evaluation method, like how do you evaluate a particular logic element by for example, a particular logic gate or flip flop like that. So, it depends that which evaluation technique that we will use, it depends on the type of logic symbols, the logic symbol that we are considering, and the type of logic elements that we have in our case. Like if all are say logic gates and say and flip flops, then maybe we will be following some we may be following some simple evaluation strategy, like say using AND or NAND NOR functions like that. If it is driven by some other bus resolution function at some point of time, maybe we have to use that. So, commonly used techniques are this one, the truth table based approach, input scanning approach, input counting approach, and parallel gate evaluation approach. So, we will see them one by one. Truth table based gate evaluation. So, this is the most straightforward and easy way to implement. So, for binary logic, we have got 2 power n entries for n input logic element. So, we can check whether a particular logic value has occurred. So, if I have got some n input function, then I may have this all 0 to all 1 cases, and for each of them I may have these values noted here. So, what is the output there? Now, for a particular, so if this is the logic block for which we are trying to for which this is the truth table. So, we can check what is the input and try to match with one of them, and whichever matches we can take the corresponding value as the output. And in fact, storing this part may not be essential, this input part may not be essential. We can say that okay, as if this is a table where I have stored only the output column, only the output column is stored here, and this input part. So, this is used as index of the table. So, this is the thing that is for we can have 2 power n entries of n input logic element. Now, we may use input value as table index. So, that can directly be used as table index, and then from there we can find out what is the value. But the problem with this Boolean table this truth table based approach is that the table size it increases exponentially with number of inputs. So, as number of inputs increases, table size also increases significantly. And particularly when we are going for multi-valued logic, the situation becomes worse, because if I have got k symbol logic system, that will require a table of 2 power mn entries for an n input logic element, where m is equal to log of k. So, for binary system, so k is equal to 2. So, our table has got 2 power n entries, but in case of k symbols, if there are k different symbols, then each of these elements it can take up each of the inputs can take up any of those k values. Okay. So, as a result, my truth table size will become 2 power mn, where m is the log of k. So, that way the table has to be, the index of the table has to be mn bit word. So, it becomes more complex. Multi-valued logic representation in truth table format will be more complex. Another way of looking into this logic evaluation is via input scanning method. So, gate output can be determined by types of inputs. If any of the inputs is the controlling value, the gate output is C XOR I, and otherwise it is the if any of the inputs is U, then the gate output is U, otherwise the gate output is C XOR I dash C prime C bar XOR I. So, for different types of gate, this controlling input and the inversion values are like this. For AND gate, controlling input is 0 and the inversion value is also 0. That means, if I have got an AND gate to be simulated, it has got 2 inputs. So, to see what is the output, what will be the output of this AND gate, we will see what are the inputs. Now, if this happens to be 0, that means we know that this has got a controlling value. So, when it has got a controlling value, the output is told to be C XOR I, where I is the inversion value. So, inversion value is also 0. So, 0 XOR 0. So, that is equal to 0. So, whenever this any of the input is equal to 0, output is equal to 0. On the other hand, if this is suppose both the inputs are 1, if both the inputs are 1, in that case none of them are controlling values. So, as a result it will be coming to this part, it is C bar XOR I. So, C bar is 1 XOR 0. So, that is equal to 1. So, in this way the logic functions can also be captured by means of this C and I values. So, this AND or NAND NOR, so these gates these are shown. So, they are actually capturing the logic symbols, the logic values by means of this controlling and inversion values. So, I do not need to store the truth table. So, for every type of gate I need to store the controlling value and the inversion value. From there by applying these 3 rules. So, we can by applying these 3 rules we can find out what is the corresponding value. So, the input scanning method, the algorithm for evaluation is like this. First, this u input is made equal to false, that is we have not seen any input which is equal to u. So, then we take the next input. So, if next input does exist, then suppose this is equal to v. So, if v is the controlling value, then we directly return C XOR I. If v is not a controlling value, then we check whether v is equal to u or not. If v is equal to u, then this u we have seen one unknown value. So, that u in is made equal to true, and if it is not so, then also it checks whether the next input is there or not. So, if any of the input is equal to u, then this u in will become equal to 1. Now, if we have not seen any controlling value, then what will happen, this input list will exhaust at some point of time. So, it will come out of this no side, then it will check whether u in is true. So, if none of the inputs are unknown input, then it will go to return C bar XOR I. So, that is the value. If it is yes, then it will return u. So, it returns 3 possible values C XOR I. If it sees a controlling value, it returns C bar XOR I. If it has not seen any controlling value, at the same time it has not seen any u, and it returns u if it has seen any of the u in the system as the input. So, this way this input scanning method, so this can compute the values of different logic elements in the circuit. Other approach which is similar to this input scanning method is known as the input counting method. So, what it does? It keeps count on the controlling and unknown input. So, C count is the number of controlling input and U count is the number of unknown input. So, it will update counts during the logic simulation. For example, if one input of a NAND gate switches from 0 to U, the C count will be decremented and U count will be incremented. So, that way it is, so otherwise the rule remains same for evaluating the gate output. So, the rules that we have here will be applicable in this one also. However, the point is that it does not do a complete simulation. So, what it will do is that suppose this NAND gate was simulated previously, this NAND gate had got a number of inputs. So, it had previously this value was found out to be 1. Now, in this method what will happen is that it will see for the next input that is coming to the NAND gate how many changes are there. Like if this it will count how many the controlling inputs are there, how many unknown inputs are there. So, if there is a change, from one pattern, so this is suppose pattern 1, from there the next pattern 2 is applied. So, it will count how many controlling values has changed, how many undefined unknown values have changed. So, that way it will be computing it. So, if it changes from 0 to u, then this modification will be done. So, at the end by just looking into the C count value, I can see that if the C count value is still greater than 0, that means the output will be C XOR I, and if I find that it is the u count value is more than c count, u count value is more than 0, and this controlling input is 0, in that case this output will be u, and if it is c count value is 0 and u count value is also 0, in that case output will be that c bar XOR I. So, that way the same set of rules will follow, but the effort needed in doing the simulation will be less, because each from one pattern to another pattern when we are going, we are just looking into the changes that are occurring in the input set. Another possible evaluation to speed up this simulation process is by parallel gate evaluation. So, it exploits the inherent concurrency of the host computer. So, a 32-bit computer, it can perform 32 logical operations in parallel. So, what we mean is, suppose I have got two operands A and B. Okay. In now this A and B, so if A is a 32-bit number, both of them are 32-bit numbers. Now, if I do a logical ANDing of A and B, okay. So, if I do a bitwise ANDing of A and B, then what will happen? So, if this is my A register, 32 bits are there, and this is the B register, 32 bits are there, then when I am doing this bitwise ANDing, so these 2 bits will be ANDed, these 2 bits will be ANDed, these 2 bits will be ANDed. So, bitwise this ANDing will be done. So, as a result, it can evaluate 32 different logic operations simultaneously, provided of course the logic operations are similar, then it can do all the 32 operations in a single shot. So, that is what is done here, that okay, suppose, so here I have got this assuming that this word size is 4 bit wide. So, so I have got, say the first input says A equal to 1, B equal to 0, C equal to 0, A equal to 1, B equal to 0 and C equal to 0. So, it can evaluate this one, so this AND gate. So, first of all this OR gate is evaluated, this 0 0, so this is 0, and then this 1 and 0, so that evaluates to 0. Simultaneously this 0, the second bit is there. So, this one and this one, so they are ORed to get this one, and then I can do this thing, I can get this OR here and then ANDing here. So, it can do 32 logic operations in parallel doing this bitwise operations. Okay. So, that way we can have much faster execution. So, we will continue with the next class.